So then the next topic for the subject is power measurement using wattmeter. So as we all know, a wattmeter is a device used to measure real power. So take note that the wattmeter, okay, so will only record or indicate, okay, so the real power absorbed, no, so by the circuit. So the reactive and the apparent power cannot be displayed, no, so by a wattmeter. So we need to perform some mathematical calculations in order for the uh, apparent power and the active power or the reactive power, okay, so to be calculated, no, so from the given circuit. So a wattmeter consists of two, okay, so it consists of two components. So one is we have there the what we so called the current coil. Okay, and the second one is the potential coil. So if you try to look at the wattmeter composition is made up of coil. Okay, so there are two coils. So the current coil, so this is where the current is, or this is where the current will flow, and the potential coil, so this is where the voltage is impressed. So if we try to draw the schematic diagram, okay, or schematic circuit of a wattmeter, so the wattmeter will look like this one. Okay, so you have there two coils. So this represents the current coil, and the one situated below, okay, so this one represents the potential coil. Okay, so the reading of the given wattmeter, okay, so this would be the wattmeter. Okay, so the reading of the wattmeter is given by, okay, assuming that we have here a current I, okay, so current I, and then uh, we have here the voltage V, okay, so across the potential coil. So assuming that this would be voltage V, then the wattmeter reading, no, okay, so the wattmeter reading is equivalent to the magnitude, no, so of the voltage V, the magnitude of the current I, okay, multiplied by the cosine, okay, of the angle in between the voltage and current. So that would be cosine of theta V minus theta current. Okay, so this will have a unit in watts. Okay, so as we progress later on, uh, although we define a wattmeter to be a device that measures the real power or the active power, but the indication of the wattmeter will also depend on the uh, position, no, position of the current coil and the potential coil. So from now on, we will have a standard configuration of the wattmeter such that the uh, current coil will be situated, no, so the coil uh, above. Okay, so this one, And then the potential coil is the coil which is below, no? So the current coil. So the reading of the or the reading, no? So of the wattmeter is vectorial. Okay, so that means it follows the what is so called this one, the magnitude and the direction, no, of the quantities that are being measured. So, for example, uh, in the current coil, so for example, in the current coil, if the or the current, no, so the current is assumed to flow from left direction to the right. Okay, so we give, no, so the standard that the current in the current coil will flow, no, so from left to right. Okay, so and also in the potential coil. Okay, so the notation of the voltage will also be given or will also be read as from left to right. Okay, so for example, in the voltmeter, I mean in the potential coil. Okay, shall we say this is connected to line A, and then this is connected to line B. So the voltage, okay, the notation must be, this should be voltage VAB. Okay, so that is from A to B. Okay, so assuming that the potential coil, no, so is okay, so let's say this is connected to line C, and then this would be connected to line B, then the voltage here must be VCB. Okay, so why is it important to have the correct notation, no, so of the voltage? Okay, so it will be used, no, so in the calculation of the cosine, no, of the angle between the voltage and the current. Okay, for the current, okay, so take note, no, for the current, the standard notation for a given wattmeter is that the current must flow, no, so from uh, the this direction to this direction, which is from left to right, no. So if you are facing the uh, computer, or if you are facing in your cell phone or your computer, so the current direction of the wattmeter must be from left to right. Okay, so what will happen if you reverse, no? So for example, you reverse the direction of the wattmeter. So for example, you have a wattmeter. Okay, so supposedly the wattmeter is this one. Okay, so you have the potential coil, the current coil, and then the potential coil, no? But then you insert, no? So by the way, how do we insert, no? So the wattmeter to, uh, okay, so how do we insert, no? So the wattmeter in order for it to indicate, no? So the real power. So the current coil, okay, so take note, no? So the current coil, this one, so the current coil must be inserted, okay, so it must be inserted, okay, so to the line wherein the current of that particular line will be measured. So for example, in a three-phase line, for example, that would be line 1 or line A, line B, and line C. Okay, so this would be A, B, and C. So a wattmeter must be inserted. For example, the current coil must be, or the current coil must indicate, no? So the current flowing in line B. So this current coil here must be inserted in line B. So what do we mean by inserted? So it must be connected in series. So this would be the location of the current coil. And of course, the potential coil must be located below. No? So this one, and that depends on where do we put the potential coil. So for example, it will be connected to line A. So then the left side, okay, or left terminal will be connected to line A. And then assuming that the second terminal is connected to line C, so it will be connected to line C like this one. So this should be the connection of the given wattmeter. Okay, so it will indicate, no, so it will indicate the reading. So for this particular position, no, so of the wattmeter. Okay, so again, no, so if we reverse, no, the current coil, so what will happen if we reverse the current coil? So like example, this would be the current coil, no? So what will happen, assuming that let's say, okay, so this is terminal, let's say X, and then this would be terminal Y of the current coil, assuming this would be X, and then this would be Y. So what if we reverse, no? So like Y is being connected to, okay, so this is B line B, and then the other one X is connected to the load, like this one. So what happens here is that upon inserting the uh, current coil, okay, so the current coil is reversed, no, of the wattmeter. So like this one. Okay, so as you can see, the current coil now is connected, no, so in reverse. So that means the current will flow from the source like this one, no, so this would be IB. So the current now will flow in this direction, IB going to, and then it will flow in this direction from Y to X, and then goes to the load. So as you can see, the current now is flowing, no, so from right to left. So with this notation, uh, the wattmeter will still indicate, no, so take note, it will still indicate the same number. Okay, so this it will still indicate the same number as with, no, so the original connection, which is B connected to X and then Y connected to the load. However, the only difference between the two is when the current coil is reversed, it will give, no, so a negative indication. So for example, if the original one indicates, let's say 700 watts, so with the current coil reversed, no, so it will indicate negative 700 watts. So the difference is just the negative indication, no, so of the power. Okay, so again, the wattmeter now consists of two coils. So the first one is the current coil, the second one is the potential coil. So the current coil must be inserted in the line, okay, whereas the potential coil will be connected across, no, so the uh, source, and then it must be vectorial, no, so that means the current coil, so when it is reversed, so the wattmeter, no, so the wattmeter will indicate negative reading, and might as well, if the potential coil, no, so is connected uh, in a particular terminal, then it must be indicated or read from left to right direction, no, so okay, so we will be, or I'll be showing you some examples on how we can, no, so how we can use a wattmeter to uh, read. no, or how a wattmeter indicates active power drawn by the load. Okay, so in this example, we're given with a three-phase source, no? So that's or with a magnitude of the line voltage, no? So given at 220 volts. Okay, so the load, no? So take note. So there is a single phase load, say, okay, connected to terminals B and C. So that's 23. Okay, let's make it 22. No? So 22 ohms connected to, okay, so that's connected to terminals B and C. So we are presented with three different scenarios. Okay, so as to the connection of the wattmeter. No? So first one, okay, so is the wattmeter reading or wattmeter indication if the current coil, no, so is connected in line C, okay, and the potential coil is in B and A, no, so take note B and A. So we may say that the, okay, so we'll just redraw, okay, so for letter A, so we have here the circuit, no, so this would be the given circuit, okay. So this should be as given, no? So that's 22 ohms. So line A, line B, and line C. Okay. The magnitude, no? So of the line voltage, that's 220 volts. Okay. So first thing we do is to draw, no? So the position, no, of the wattmeter as indicated. So in letter A, so the current coil, no, so is in line C. So how do we position the current coil? So it must be connected, no, so or inserted, no, in line C. So therefore, we have here the current coil, no, so which is inserted in line C. Okay, and the potential coil, okay, so which will be okay, so that is the second coil below the current coil. Okay, so this one. So take note that the potential coil is in B and A. So again, we follow, no, so the notation from left to right. So that means the left terminal of the potential coil is in B. Okay, so that's it's connected in B. Okay, so we give, no, so the connection as in the circuit, no, so with the symbol dot. Okay, so without that connection, that means it's not connected. Okay, okay, or you may opt to use this notation. Okay, so let's say you do not want to use that. Okay, so you can also use this notation. So the jumper, no, so that's connected to B, and the right one, this one, right terminal that's connected to A. Okay, so okay, so then this should be the wattmeter, no? So wattmeter as position, no, in letter A. So how do we calculate, no? So the wattmeter reading, okay, for letter A, so uh, you still need, no, so we still need to what we call this one plot, no, so the phasor of the voltages and currents, no, so that is a must in three-phase analysis, no, so that means we have to plot the line-to-line voltage. Okay, so assuming we have positive sequence, okay, so this would be the phasor, no. Okay, so we have there the voltage VAB. Okay, so this would be voltage CA, and of course this is BC. Okay, separated by 120. No? So 120 electrical degrees. Okay, assuming that we have here a current, no? So assuming we have here a current, let's say IBC, no? So such that we can calculate, no? We can calculate IBC. So that's VBC divided by 22. So IBC then can be calculated as, okay, so if you try to look at VBC is situated at, uh, okay, so that's 220 angle negative 120, no? So divided by 22, so therefore IBC is equivalent to uh, 10. Okay, so that's 10 angle negative 120. So in terms of ampere. So we give, no, so the following notation. Okay, so this would be current IA. So this would be the current IB. And of course, this would be the current IC. Okay, so we'll be using this Okay, so the current, no? So the current drawn by the load, no? So when we calculate for the reading, no, of the wattmeter, okay? So for letter A, so with the current coil in line C, potential coil in B and A, so we then say, no? So we then say that in letter A, the wattmeter reading is equivalent to, so the magnitude of the voltage VBC, okay, sorry, that's VBA. Okay, so why VBA? Because it's connected to B and A, no? Multiplied by the magnitude of the current IC. Okay, so why IC? Because the, as you notice, no, so that's in line C, no, so the current coil is in line C. Okay, so multiplied with, okay, so that's multiplied with the cosine, no, so cosine of theta V minus theta current. Okay, so the wattmeter indication is the magnitude of VBA, that's 220. So although VBA is situated or graphically, no, the phasor of VBA is the opposite of AB, but the magnitude, no, the magnitude of AB and BA, so it's actually the same, but their direction is opposite, no. So the current IC, okay. So as you can see, the current IC, so obviously IC is the negative of IBC, right? So if you try to take KCL here, so IC plus IBC is equal to 0, or basically IC is equal to negative of IBC. Okay, so but we want here the magnitude of IC. So the magnitude of IBC is 10, right? So that's 10. Then cosine of, no? So that's theta V. Okay, so by the way, where is IC? So if we calculate, so that's negative of 10 angle negative 120. So we can have IC, that's 10. Okay, so if we try to look at, uh, okay, so you can input directly, no? So in your calculator, just put the parenthesis sign. Okay, so that's negative of 10 angle negative 120. Okay, so you will be given with 10 angle 60. Or graphically, we can say that IBC, no? So as you can see, IBC is uh, or can be plotted, no? So as in phase with the voltage VBC, such that IC is the negative of, no? So when you say negative, that is the opposite of. So this is IC, so which is negative of IBC, no? So this one. So which will have an angle of 60, but the same magnitude, no? So as you can see, no? So when you input this in your calculator, so that is cosine of theta V. Okay, so that's theta of the voltage. That's what is VBA, no? As you can see, that's 180. Okay, minus theta I, so that's 60 degrees, no? So you will have a reading of 220 times 10 times cosine of, okay, so that's negative, okay, so we'll have it here. Okay, so the wattmeter reading is negative 1100 watts. Okay, so do not be surprised, no? So with the negative value, there is no such thing as negative power in uh, electrical engineering. No, so the negative in the answer is just the indication. No, so the power drawn of the circuit is always positive, but because of the positioning of the wattmeter may indicate. No, so it is just an indication. That is not the power drawn. No, so that is not the power drawn by the circuit. Okay, so it is just an indication of the wattmeter. So the wattmeter with the position as indicated in A will have a reading, no, so of negative 1,100 watts. Okay, so we now go on to the second, no, so the second case, which is the current coil in line B, potential coil in A and C. Okay, so just erase everything, no, so that we can okay, so with the second case, okay, okay, so for the second case, that is for letter B, no, so we try to redraw again, or we try to redraw the given circuit. Okay, so with the load as indicated, that's 22 ohms. So this would be A, B, and C. Okay, so the current coil is in line B, no? So meaning to say we have here the current coil. So inserted in line B. Okay, so of course it will take, no? So the the current coil, no, so will, or the current that will flow, no, in the current coil is obviously the current in line B, IB, no, so okay, and then the potential coil is in A and C, no, so we have here the potential coil that is in A and C, so you have there A and C, okay, and then this would be the wattmeter, okay. So how do we obtain, no, so the reading of the wattmeter? So you will see that uh, there is, no, so a difference in the indication, no, of the wattmeter uh, from letter A to letter B. So the reason of which is the position, no, positioning of the potential coil and the current coil. Okay, so we can have, no, so um, this would be, of course, no, so this is line B. I'm sorry, it's IB, and the potential coil will indicate voltage A to C, no, and then this would be IBC, no, so as indicated. Okay, so obviously we can say, no, so we can say that in letter B, IB is of course equal to IBC, no, so it's very clear that the current IB that will flow here is the same as the current IBC, no. Okay, so that is equivalent to 10 angle negative 120 degrees ampere. Okay, so I'll just erase this one. Okay, and then we can, no, so we can calculate the reading of the wattmeter, no, so the wattmeter reading for letter B is voltage AC, the magnitude of the voltage A to C, the current, of course, no, IB, and then cosine of the angle theta V minus theta current. Okay, so the wattmeter reading is the magnitude of AC. No, so where is AC located? So AC is the opposite of CA. Okay, So this would be VAC. So this is 60 degrees, no? Okay, so that's 220. Still, the magnitude is 220. But again, as I mentioned, that's opposite of CA. So the magnitude of current IB, that's 10. Then cosine of, no? So theta V. So that's, okay. That's cosine of, okay, so that's VAC, that's negative 60. Okay, so that's negative 60 minus theta I. Okay, so for the current, that's, okay, so try to take a look at the current. IB is the same, no? So as with IBC, that's minus negative 120. Okay, so such that the wattmeter reading for the given, okay, position, that's 10 times cosine of negative 60. Okay, so the reading would be 1,100 watts. Okay, so that's actually no, so different from A. Okay, so what is the factor that the reading in B is different from A? So the answer is the position, no, of the two coils of the wattmeter. So meaning to say that the positioning of the wattmeter will have a great, no, so effect of its indication. Okay, so that's 1,100 watts for B. Okay, so and here comes letter C, no? So the current coil, no? So it's in line A, potential coil is in B and C, no? So we'll just erase, no? So let me erase this one. Okay, so and then while doing this one, you try to guess, no? So what would be the reading, no, of the wattmeter when it is positioned as indicated in part C. Okay, so have you had your guess? Okay, so anyway, let's try to calculate, no? So that would be line A, line B, and line C, no? So this would be A, B, and C. And then the load is indicated, let's say 23 ohm, 22, no? So that's, okay, so that's 22 ohms. Okay, so that's 220, no? So the magnitude of the voltage line to line is 220 volts. Okay, and now as indicated, so you have there the wattmeter, so with the potential coil in line A, this one, and then I mean the current coil, no? So it's in line A, and then the potential coil is in B and C. So B, and then you have there C, and this would be the wattmeter, no? So as indicated. So obviously, we have here the current that flows in the current coil, which is IA, and then you have the potential B and C. No, so such that we can have the wattmeter reading as indicated. No, so that's voltage BC, current IA, cosine of the voltage minus, I mean theta, no, for the voltage BC. So we just say VBC, so that's uh, 220. Okay. IA, on the other hand, obviously is if you try to look at, IA is of course zero. No, so why zero? Because the other end, no, so it's not connected to the load, no, so meaning to say that the current IBC will just circulate, no, so it will just circulate in terminals B and C, no, so this one, but the current IA here is of course zero, no, so because this is open, and then anyway, so you may not uh, dig, no, so what would be the value of theta V and theta I, because the current here is zero, no, so obviously the answer is okay. So obviously the answer is of course 0 watts. Okay. So as you can see, no. So when we uh, place a wattmeter, no, so in a circuit, so depending on the orientation, no, so of the wattmeter, it may give a different reading. So, but that doesn't mean that the wattmeter, no, so the indication of the wattmeter is the uh, total power drawn by the circuit. Okay, so the next question now is how do we uh, put, no, so or how do we arrange wattmeter such that the indication, no, the indication of the wattmeter will be the actual, no, so the actual power drawn by the circuit. That is actually the most important part, no. So we do not want, no, so we do not want the indication of the wattmeter that is not the actual power drawn with the circuit. Okay, so that is why we use a wattmeter, because we want the device, no, so to indicate how much is the real power, no, or the actual power drawn with the circuit. So the question is, how do we arrange, no, or how do we connect wattmeter in such a way that it will indicate, no, so it will indicate uh, the real power, no, drawn by the what they call this one, the three-phase load, no. Okay, so that would be our next topic, no? So uh, how do we indicate, no? So okay, let me clear. Okay, so for three-phase, for three-phase circuit, okay. So we have the what we so called two wattmeter method, no? So which can be used to uh, determine, no, so the total power drawn by the uh, load. Okay, so okay, so we have here two wattmeter method. Okay, so in a two wattmeter method, of course, you will be using two wattmeters, no? So meaning to say, uh, in order for the wattmeter not to indicate real power drawn by the circuit, it must be connected properly. And then the common, no? So the common configuration that is used uh, in practicality is the two wattmeter method, no? So we employ two wattmeters to measure power in a given what we call this one, three-phase circuit. And then what we do is we uh, have some mathematical computations. Okay, so that will indicate, no, so the total power drawn by the entire circuit. Okay, so in the two wattmeter method, So we will have the following notation, no? Okay. So assuming that we have here balanced load, no? So, or how do we, by the way, how do we arrange, uh, how do we arrange the wattmeters, no? Or how do we arrange the two wattmeter or wattmeters, no? In order for it to, what we call this one, to indicate, no? So the total power drawn with the circuit, no? So now two wattmeter method will be configured either any of the three scenarios, no? So assuming you have their um, okay, let's say you have their three-phase source, no? So with lines A, B, and C. Okay, so the first scenario, okay, is that you have their line A as common. Okay, so meaning to say, line A would be common. That means the current coil of the two wattmeters will be in line B and C. Okay, so meaning to say, we do not uh, connect, no? So the potential coil of the wattmeter to the common point, no? So which is line A. So wattmeter one, of course, now you have the wattmeter one, which has its current coil in line B, and then of course the second wattmeter, okay, so we'll have its current coil in line C. Okay, so this would be the current coil of wattmeter 1, and then this would be the current coil of wattmeter 2. No? So if you have there the common point, so you have to avoid having the wattmeter, no? So in that given common point. Okay. Now, as indicated from the previous discussion, no? So that the potential coil will be placed, no? So directly below the current coil, no? So such that the potential coil, like this one, no? Okay. So since line A is common, okay, so we then say that the potential coil, take note, no? So the potential coil must be connected to the uh, across, no? So it must be connected across the line. So wattmeter 1 will have, since the current coil is connected in B, then the terminal of wattmeter 1 for its potential coil will be connected to B also. So that is in line B, whereas the other one, this is connected to line A. Okay. Might as well with wattmeter 2. Okay, so since the current coil is connected in line C, then the potential coil, one of the, or the left uh, side, no, of the potential coil will be connected to line C, and then the other one, okay, so is connected to line A. So this one, okay, so that is uh, line A. Okay, so line A as common point, that means that is the common point for the potential coil, no? So with the what do you call this one, with the current coil situated, no, situated in the other two lines, so line B and C, no, so in this case, because line A is set as common. So we then say, no, so we then say that this would be wattmeter 1, and of course, this would be wattmeter 2. Okay, so we give, no, the following notation: wattmeter 1, that is uh, voltage VBA IB. Okay. Cosine of theta VBA minus theta IB. Okay. Wattmeter 2, on the other hand, will be noted as VCA. No? So, and then multiplied by IC cosine of theta VCA minus theta IC. No? So the unit of force in, okay, the unit is in watts. Okay, so later on we'll try to identify how do we obtain also the reading of the power drawn by the three-phase, assuming you have there a three-phase load, no? So how do we obtain the power drawn by the three-phase load using two wattmeter? Okay. So the second scenario, okay. So the second scenario would be uh, okay. So the second scenario is case two, no? So with line B as common. Okay, so in this case, you have there three lines. It would be A, B, and C. Okay, so with line B as common, so this would be the common point. So the wattmeters or the current coils now of the wattmeters will be inserted in A and the other one in C, right? So this would be wattmeter 1, and then this would be for wattmeter 2, okay? So how do we arrange the potential coil? So first you need to draw the potential coil of the two wattmeters like this one. So the potential coil is connected for wattmeter 1 in A itself, and then the second terminal is in common point. For wattmeter 2, it will be connected in C, and then it is connected to the common point like this one. Okay, so and then you have there the 2. Okay, so for wattmeter 1, that is voltage AB, current IA. No? So assuming you have their three-phase load, okay, connected. No? So that is VAB IA, no? And then cosine of theta VAB minus theta IA. No? So and then wattmeter 2, on the other hand, will be or will have no reading of the magnitude of VCB multiplied by the current IC cosine of theta VCB minus theta IC. So again, no, both of these will have a unit in watts. Okay, so what would be case three? No, okay, so case three. So where do you think is the common point? Okay, so I think you have it in your mind right now. That is in line C. No, so case three. So with line C as common point. Okay. So what is line 1, A, B, and C? So this is A, this is B, this is C. No? So again, no? So assuming we have here three-phase load. So what do we uh, do next is to connect, no? So the two wattmeters. So C is the common point. So obviously the current coils of the two wattmeters are so in line A and the second one in line B. Okay. So the potential coil of wattmeter 1. So this is wattmeter 1. So this will be connected to A and the other one in C. For line B or wattmeter 2, so the left terminal is connected to B, and then the other terminal will be connected to C, like that. No? So then this would be wattmeter 2. So uh, the readings, no, so can be calculated as, no, so that would be wattmeter 1 VAC, current IA, no, so cosine of theta VAC minus theta IA. Okay. Wattmeter 2 on the other hand, that would be VBC. Okay, so current IB cosine of, no, so that's theta VBC minus theta IB. Okay, so of course, now this will have a unit in watts. Okay, so okay, so now we do have, no, so the connections for the two wattmeter methods, no, as to how would we connect the two wattmeters in order for the wattmeters to indicate, no, so the total power drawn by the circuit. Okay, now the next question is, after obtaining, no, so after obtaining the uh, okay, so after obtaining the total power drawn by the circuit, I mean the obtaining the reading, no, of the wattmeter. So how do we get, no, so the total power drawn with the circuit once we have the reading of the two wattmeters, no? That would be the question, no? So given that you have already have the uh, indication, no, of wattmeters 1 and 2, either in case 1, case 2, or case 3. So how do we, what you call this, and how do we obtain, no, so the uh, total power drawn, no, so by the circuit? Okay, so okay, uh, let me have some short derivation, no, as to how we obtain, no, so the total power from the wattmeter readings. Okay, so we'll just use let's say, okay, so assuming, no, so we have here a Y connected load. Okay, so whose impedance is Z. So uh, okay, so assuming you have their impedance Z with lagging power factor, no? So let's say you have the lagging power factor of the load, no? So this is A, B, and C. Now let me have, let's say, we'll use case 2, no? So with the potential coil in B, common point, no? I mean common point, no? So you have their wattmeter 1. Okay, so this would be the positioning of wattmeter 1. And then the other one, you have the wattmeter 2, no? Okay, so you have the wattmeter 2. Okay, so common point is B. Okay, so this is wattmeter 2, no? So and then this would be wattmeter 1. Okay, so um, if we, no, so if we let's say obtain, no, so wattmeter 1. Okay, so wattmeter 1 will have a reading of V. Okay, that's AB, IA. Okay, so cosine of Okay, so that's theta VAB minus theta IA, no? And also with wattmeter 2, that's VCB IC, no? Cosine of theta. Okay, so this is VCB minus theta IC. Okay, so and okay, so so first is we need to plot, no? So plot the base source, no, for the voltage and current, voltages and currents. Okay, so so we will have, no, so the following. Okay, so for this would be IA. This one is IC. Okay, so this would be, of course, no, so shall we say IAN, IBN, and this would be ICN. Okay, so we denote, no, so we denote. Okay, so this would be also IB, no, so we denote IA, that is equal to IB, that is equal to IC. So these are the line current, no, so and then for the for the per phase current. Okay, so we also denote, no, so the following IAN, that is equal to IBN, that is equal to ICN, that is equal to the per phase current. Okay, the per phase current IP. Okay, so if we try to plot, no, so if we try to plot now the phasor, no, of the voltages and current. Okay, assuming that we have here a lagging power factor for the load, then we can have, okay, so we'll have the following phase source, no? So for the voltages, so we have here VAB. Okay, so assuming you have their positive sequence, no? So VCA and okay, that is VBC, no? So and then for the okay, so for the per phase voltage, okay. So remember the per phase voltage will lag, no? So by 30 with respect to the okay, so this would be AN. Okay, so this would be CN and this would be VBN, no? So it will lag by 30 degrees, no? So with respect to the line voltages. Okay. Now assuming okay, so take note, no? So assuming that we have a lagging power factor, no? So we denote, no? So the power factor. Okay, so we denote the power factor as uh, okay. Let us say we denote power factor equals to cosine of theta. Now, so remember, theta is the angle between this would be the angle between VP and IP. No, so since we have a lagging power factor, so we then say that the current IAN lags. No, so by an angle theta. Okay, so with respect to VAN, and let us say the current ICN lags, no, with an angle theta with respect to VCN, no? So and then you have it there the current, no? So current uh, let's say IBN, it lags, no, by an angle of theta with respect to the current or voltage VBN, no? So again, no, so the power factor angle is the cosine or the power factor angle, no? So is the angle in between VP and IP, no? Okay. So we then say, no? So we then say that from the phasor, okay, so we can calculate, no? So the reading, wattmeter 1, Okay, so wattmeter 1 can be written as the magnitude of VAB, no? So the magnitude of VAB is VL, no? So that is the line voltage. IA, on the other hand, so the magnitude is equal to IL, and then cosine of, no? So that is theta VAB. Take a look, no? So theta VAB, this one, so that is 0 minus theta IA. No? So as you can see, theta IA is equal to IAN. No? So because we have a Y-connected load, IP is equal to IL, right? So theta IAN is equal to 30 plus theta. Okay, so the angle here, this one, okay, this is equal to 30 plus theta. Okay, so this would be the indication of wattmeter 1. So that is VL IL cosine of. Okay, so that is negative of 30 minus theta. No, or basically we can have okay, that's uh okay, so let me erase. Okay, so you have there 30 plus theta. Okay. So okay, so that's I'm sorry, that's negative, no? So negative 30 minus theta. Okay, so that's actually this is negative. Okay, so that makes it positive, no? So okay, so let me rewrite, no? So to make it clear. Okay, so that is 0 for VAB minus this angle here is 30 plus theta, but since it is situated, no? So below the reference angle, so that is negative of 30 plus theta. So that makes it positive, no? So, okay, so we can have, okay, so we can have cosine of 30 plus theta. Okay, so this would be the indication of water 1. So line voltage, line current, cosine of 30 plus theta. So what in your theta is the power factor angle. Okay, for wattmeter 2, okay, so wattmeter 2 is equivalent to the magnitude of VCB. So that is VL, the magnitude of IC. Okay, so take note, it is equivalent to IL. And then cosine of, no? So if you try to take a look at theta VCB. So where can we found VCB? Okay, theta VCB, okay, so can be found here. Okay, so that's the opposite of, okay, so this is VCB. Okay, so the angle here is 60. Okay, and then take note, the angle between VCN and ICN is uh, theta, no? So this one. Okay, so VCB on the other hand, that's actually 60 degrees, no? And then ICN on the other hand, no? So the angle for ICN, that is this one, no? So let me have the different colors. So this should be 90 minus theta. Okay, so this is theta. So first this is 90 minus theta. So this is minus the angle which is 90 minus theta, right? Okay. So therefore wattmeter 2 can be written as VL IL and then cosine of. Okay. So that is negative, okay, so 30 plus theta. Okay. So Okay, so we then say that uh, for a balanced load, okay, so for a balanced load, the indication, no, so as I've said, no, so we have two wattmeters. So the indication of wattmeter one of a balanced load is VLIL cosine of 30 plus theta. And the indication of wattmeter 2, no, so is given as VLIL cosine of negative 30 plus theta. No, so meaning to say, there will be no more problem as to balance load because we have already established, no, that the reading of the wattmeters, regardless who is the common, so wattmeter 1 will have an indication of VLIL cosine of 30 plus theta, and then wattmeter 2 will have VLIL cosine of 30 minus negative 30 plus theta. Okay, so let me clear this one. So again, no, for balanced load, so wattmeter 1, that is VLIL cosine of, let me have theta first, no, plus 30. And then wattmeter 2 will have an indication of VLIL cosine of theta minus 30. So obviously this will be, or this will have a unit in watts. Okay. So take note, this is for balanced load, no? So how do we obtain the total power? Okay, so if we add, okay, so what will happen if we add wattmeter 1 plus wattmeter 2? So you will have VL IL cosine of theta plus 30 plus VL IL cosine of theta minus 30. Okay, so you have to memorize these formulas. No? So because you can use these formulas directly to um, subtract, I mean, obtain, no? So the reading of the wattmeters, no, particularly if your load is balanced, no? So all you need to do is to obtain the line voltage, the line current, and the power factor, and then substitute. You don't have to you don't have to write the positioning of the wattmeters, no? So just to obtain the reading. Okay, so let me continue. That's we can factor out VLIL. Okay, then this is cosine of theta plus 30 plus cosine of theta minus 30. Okay, so now using the identity, no? So identity from your trigonometry, so you can have uh, this one can be expanded as cosine theta cosine 30 minus sine theta sine 30. Okay, and this one plus this cosine theta minus 30. So this can be calculated as cosine theta cosine 30 cosine of, okay, so that's 30 plus sine theta sine 30. Okay, so we can cancel out this one together with this one, no? So such that your wattmeter 1 plus wattmeter 2, that is VL IL. So times 2 cosine of theta cosine of 30. Okay, so this one and this one can be added. So such that wattmeter 1 plus wattmeter 2, that is, if you calculate directly 2 cosine of 30, you will have an answer of square root of 3 VL IL cosine of theta, which is actually, if you try to look at, this is actually the three-phase power formula, no? So meaning to say, by practicality, you can use two wattmeter method to uh, obtain, no? So the total power of the circuit by adding the reading of the two wattmeters, no? So as you can see, the reading of the or the total power drawn with the circuit is equivalent to the sum of the reading, no, for the of the two wattmeters, no. So and then if we try to subtract, no. Okay, so if we try to subtract also uh, okay, wattmeter 1 minus wattmeter 2, so obviously this will cancel out the cosine theta and cosine 30. Okay, so let's say, no, we subtract wattmeter 2 minus wattmeter 1, no. So what will remain is VLIL and then 2 sine of, no. So theta sine of 30, no. So the cosine theta and cosine 30 will cancel out. Okay. And then this will result to VLIL and then multiplied by sine of theta. Okay, so 2 sine of 30 is 1. Okay, so if you try to look at, if we multiply square root of 3 times wattmeter 2 minus wattmeter 1, this will result to square root of 3 VL IL sine of theta, which is actually the reactive power of the circuit, no? So this would be three-phase power. So you multiply square root of 3 times the reading, no? So the wattmeter 2 or the difference in reading between wattmeter 2 and wattmeter 1, you will have square root of 3 times square root, VLIL sine of theta, which is the reactive power, no? Okay. So the reactive power can be calculated by multiplying square root of 3 to the difference, no, of the reading from the two wattmeters. And if we try to look at the power triangle, so this is S, this is P, this is Q, this is theta, no? So such that if we want to calculate, no, the power factor of the load given the two reading of the wattmeter, so we can have tangent of theta, that is the opposite, no? So Q, sine over cosine, no? Q over P. Okay. So Q is equal to square root of 3 wattmeter 2 minus wattmeter 1 divided by P, that is wattmeter 1 plus wattmeter 2. Such that the power factor angle actually is the inverse tangent of, okay, square root of 3 multiplied by wattmeter 2 minus wattmeter 1 divided by wattmeter 1 plus wattmeter 2, no. So this is how we obtain, no, so the reading, no, of the or the power factor. Okay, so the significance of this one is in actual we can measure, no. So in actual, you do not need to bring your calculator, no. So just to calculate the power, the reactive power. So what is used in the actual, no? So or practicality is the wattmeter, no? You connect the wattmeter. Okay, so the two wattmeters. Okay, so it's either case 1, case 2, or case 3. You obtain the reading of the wattmeters, no? And after after obtaining the reading of the two wattmeters, no? So you add the reading, that is the total power. You multiply square root of 3 to the difference, that is the reactive power, okay? And then you can calculate, no, so the power factor of the circuit using, no, so the uh, reading, no, so of the two wattmeters as given, no, that's square root of 3 wattmeter 2 minus wattmeter 1, okay, so divided by wattmeter 1 plus wattmeter 2, okay. So that's how we calculate, no, so the total power, okay, so of the circuit. Okay, so given the wattmeter reading, okay.